Hello students, today we will discuss electric flux, a new concept of today's video 17, same chapter electric field. To understand this concept, as usual we have to go through thoroughly at least last two videos. In the last video, previous to that, I discussed in detail about electric field, properties of field lines. If you write a directed line segment in a particular direction, what does it mean? All that you learn. So based on that, we will continue our discussion on electric flux, an important idea to understand Gauss theorem and its applications, which involves the concept of electric flux. First of all, what is the meaning of the word flux? The English word, in fact a Latin word, means to flow, to flow. Flux means to flow. That's why I have written a diagram to let you know clearly, understand. It's not in our NCERT book, but it gives a clear understanding, visualization of the word flux, to flow. See students, this is a rectangular pipe, usually water carrying pipes, cylindrical. I have chosen rectangular to make the concept more clear, the understanding of concept more clear, right? Here, these lines, stream lines, represent what? The water flow direction, water flow. Water flows in my example to the right, coming out of this cross section. So I can call water flux. What is this? Water flux, right? Now I'll choose a very small cross section, a very small unit, right? Rectangular, let's say. It doesn't seem to be rectangular because you are observing from a side view. You are observing from side. This seems to be shorter than this, but it's rectangular. Let us suppose rectangular. Square, length, breadth, both are same. Now, if the water coming out of this cross section, in a given time, say 1 second or so, any time you can take 1 minute, 1 second, per unit time, water that comes out, flow in this direction is V. What is V in our discussion? Volume rate. Volume rate means amount of water coming out, maybe in ml, amount of water in ml, milliliter. Water rate means per second, volume rate per mm square, you like that, per mm square, 1 mm length, 1 mm breadth, a square unit. Let us suppose V is the value coming out, say some 10 ml, 1 ml, like any value you take. But the point is, how much water flows through this mouth in a given time, since you know value flowing across one each unit, a small dot, V. It's very simple. First of all, before I come to that question, I'll outline this mouth to visualize the concept clearly. What is this? Why a yellow line now? Yellow line is a frame, rectangular or a square frame. I have placed a frame exactly same size as that of the mouth. Right? What is the area of this? Area is area of cross section of this yellow frame having same area as that of the mouth of the pipe is A. Now the question is very simple, common sense physics. What is total flux? Total water flux across the area. Let me denote by phi. How do you find? Yes, very simple. At each point, the smallest square, value is V. At each point is V. Then what is the total value through the entire area? Very simple. Value at one point into area. Value at one point into area. That is water flux. Very simple, right? As simple as a small calculation, like if one mango costs 10 rupees. What is? It is per rupee. What is total price of 50 mangoes? The value is 500. Total value, total amount, total flux. Value of one mango, price of one mango into total number. volume at one point into total area. Volume at one point. One point has some unit area like 1 mm square. Any value you can choose. So very simple. See students, here which way water is flowing and how you have held the area. Second word, how you have held the area. That is very important here. Now, the area of cross section is perpendicular to direction of flow. Let us suppose there is let us assign a direction to the area. Let us suppose this orange arrow is the direction of the area. Initially at this stage may look strange. How sir you assign a direction to area? Because you have assigned direction for our complete explanation for the quantities like force, velocity. If I assign direction, force has a sense. Applying force this way, that way, this way, right? It has sense. But does area, assigning direction to area have a sense? Yes, we'll know that. Now you just think like this before I come to that point. See, this is area of cross section. Now I have assigned direction to the area. Now if I consider area in this direction, our explanation will be more clear and precise. Students, I am assigning direction to the area. How? Area perpendicular. This is normal. It is also called normal to the area. What is this? This is normal. Just observe carefully. Normal. What is n? N cap. I write here n cap is normal to area. What is normal? Normal is perpendicular. Normal means what? I write here. Normal means perpendicular to area of cross section. To this area of cross section, n cap is perpendicular. To that direction, flow is parallel. When the flow is parallel to the normal to the area. Look, understand this word carefully. This blue piece of chalk represents flow and this normal, both are in the same direction. So what's the angle? 0. That's what you have to remember now. It's very simple. Now the point is, if I lift the area, which one? Orange. If I lift this orange area a little bit to a angle, what happens to the flow? Flow through the area. See here, it is like this. If I lift it up somewhat like this, I'll write diagram using another color, orange. See students, I'll use pink. Look here, I am lifting the area a little bit up to a bit larger angle so that you can easily realize it. See, almost same length. See, this is the new orientation. New orientation of what? The same area of cross section. New orientation of same area of cross section. See students, can you understand anything out of this? Yes, definitely you must. What is the direction of flow? Let's come to this point. Where is the normal now? Yes, normal is here. Not is normal, perpendicular. This is perpendicular to the area. This is n now, new n, normal to the area. What is the direction of flow? Flow remains the same. Direction of flow of water remains the same. This is also flow, right? Flow here and here, both same. But the thing is, the effective area available for flow is less. How do you show that? Just you draw this corner over this. Draw a line from here. Just perpendicular. Do the same to this, right? Then you draw, join these 2 points. See, now I'll shade this color. Look here, I'll shade this color. This white portion is the area through which water flowing below this cross section or below this area. Since I lifted the area, look here, very simple. You think like this. When I hold it like this, entire water flows. When I lift it up like this, water below this region flows outside the area. Entire water is not flowing. Very, very important thing this, right? to make you understand even better, right? I'll consider this here. Only this edge I consider. This edge and this edge. These two edges I'll consider. This is the initial position of the area of cross section. This initial position. The entire length is A. The flow of water here is V per unit. Now I lift this area to an angle. Okay? Same length, almost same length. Same length I am measuring. Right? Same length. Now theta is the angle. You extend this end perpendicularly over this, called projection. Find the projection of this over this. We have learned in last year's vectors chapter, projection. If you draw a line perpendicular from the tip here down, projection. Only this edge you are, look here, you are looking at the area like this. This is the area. Front view, side view. You are looking at this edge, only edge. If I lift it up to an angle theta, look here, to an angle theta, almost same length. See, only this much area is available for flow. Below this, flowing outside the area. Understood, students? You have to think like this. This is how you have to think. If you don't think, get things by heart, you score good marks in board exam. In CET and other areas, the performance will be low, right? We have to think like this. Now, what is the effective area available? What is area full? Same as this. This is A. Full, this also A. Look. A. Now, this is with respect to this opposite side. Area wise, opposite area I can say. This adjacent area. This hypotenuse area. Right? For area, last year you wrote right angle triangle with sides and applied trigonometry, right? Sin theta, cos theta, tan theta, like that, several terms you define. Now you are doing the same for surfaces, 3 surfaces, 1, 2, the other one, third like this. This is the third one. One area, second one, third one. 3 areas. Now, what is the value of adjacent area? Say very simple. I'll write this here. What is adjacent area? Adjacent area is equal to hypotenuse area into cos theta. All of you know why. Adjacent equals to hypotenuse cos theta. Cos theta is adjacent by hypotenuse. As you are calculating areas, effective area available, I write A for area adjacent. That's equal to hypotenuse area, which is A, into cos theta. Similarly, if you want opposite side, what is opposite? Hypotenuse into sin theta. But for area opposite, what do you write? A sin theta. This is of no use in our calculation. You can write like this. If it is required, you write. It is not required for our calculation. Now students, if the area initially like this, entire water flows. If you lift the area a little bit like this, only part of the area is available for flow. What is that part? A cos theta. What is that? Adjacent. Only this part is available for water flow. What is the meaning of this? Water that flows below this line, outside the area, it is flowing. Above this line, flowing through this cross section, as it is slant, only water that enters this region will flow through this area, right? That is adjacent side area with respect to this, as it is slant, inclined. So, the new area is A cos theta. Students, has flux changed? Definitely, because area is tilted like this. Only a part of the initial value this. Now, only a part is available for flow. Flux changes. The point is very simple. If area is turned through an angle theta, then new area available, new area available for flow. What is new area available for flow? A cos theta. A initial value, it is A cos theta. Therefore, what is new flux? New flux phi dash I write, that is value per unit area of cross section V only. So initially when area was like this, yellow, water flowing per unit area of cross section V. In this position also V, but the effective area less. So into effective area, not A, this time it is A cos theta. This is the new flux. Students. Now let me use that normal. If you turn this through an angle theta, this edge you can observe. With respect to the flow direction, here the angle of rotation theta only. Initially they were in the same direction. Look here, very simple. See, here the blue represents direction of flow. This normal, right? These two are the same direction. Yeah. With respect to this, water is flowing across this perpendicular to the area. Now if I turn this through, right? Turn this through an angle. Yeah. This is attached to the area normal, but the water flow remains the same. Water flow remains the same. It is flowing in the same direction. Only area has turned. That's why the new area is like this. Water flow in the same direction only. You have turned the area which was like this through an angle theta. Therefore, normal also has turned through an angle theta. Students, if I use a direction normal to represent area, what do you think? If I hold piece of chalk, students, area is like this. What do you think? Area of cross section is like this. Like this. This normal is horizontal, area must be vertical. If I hold it like this, area must be like this. I am not showing the area of cross section, but you have to think, we have to visualize like that. If I hold normal like this, where is the area? Normal is vertical, area must be horizontal, right? So, representing area with a normal has an advantage here. What is that advantage? I can explain you how the area rotates with respect to initial position by observing the angle between the horizontal and this new direction perpendicular to the area. That is normal, new position of normal, right? So this is initial position of the normal, this is new position, right? This is new normal. What is the direction of flow initially? This theta is equal to this theta. Both are same, right, students? So this is new expression, and this explains all the behaviors. Phi dash equals to A into V into cos theta. You can write AV cos theta or V into A cos theta. And this is a general expression. What's the meaning of that? If I hold the area to any angle with respect to this, like this, like this, like this, like this, even like this. Even like this means the area here is parallel to the flow. Area is parallel to the flow. When area is parallel to the flow, what is the angle? When the direction of flow and direction of the area is are parallel, then what is the angle? Very simple. As I told you, this is horizontal direction of flow. This is vertical, normal. What is the angle between them? 90. If I hold area like this, normal to the area, pink color chalk piece, perpendicular to the area, the angle is 90. When I hold it like this, here the normal and direction of flow both are same, the angle is 0. Here the flux is maximum, entire water is flowing through. As the angle increases, the flow through this area, decreases. So see here, students, below this portion flowing outside the area. If I bring it down little bit, the angle decreases, the flow increases. Area available for flow increases, effective area. If you increase the angle, effective area decreases. If you hold parallel to the flow, no area available for flow. Naturally, flux must be 0, right? So if you put different values for theta, that gives corresponding flux. Theta 0. What is theta 0? You think like this. Here, direction of flow, normal or in the same direction. Theta 0, cos 0, 1. Therefore, cos 0, 1 implies cos 0, 1. Theta 0. Theta 0 implies cos 0, 1. And that implies what is phi? Phi equals to V into A. Cos 0, 1. Theta some 60. Theta some 60. In that case, what is cos 60? Cos 60 is half. Then what is phi? Phi equals to VA into cos 60 half. Half of VA. Half of VA means what? For example, this angle is 60. Only half of the area. Half of the full area. Full area is this much. Only half is available for water flow. See? What happens here? Written mathematically. Then the third one is very interesting and you can easily realize it. Theta equals to 90. What is cos 90, students? You have learned in your regular class cos 90 is 0. Therefore, what is flux? Flux phi equals to 0. Is it true? Yes. If water is flowing like this, if I hold entire water flows through this. This is 0 angle position. Once again, 0 angle means what? Normal and the direction of flow. When I hold it like this, water is flowing like this only. If I hold it like this, what is the angle between normal to the area and the direction of flow? What is the angle between these two? Angle between these two is 90. What is cos 90? 0. Cos 90 0 implies flux 0. Flux 0. So this expression explains how the flux through this area changes with angle. Students, unlike numbers, I wrote a value 1 mango 10 rupees into 50 mangoes gives 500 rupees. That's 500 only. But here, value of water flowing through each cross section, smaller one, V into area A is not a constant. It has a special property that the value VA changes with orientation of the area. If you call this product flux, rightly so. Why? Because this represents an outward flow through this. Outward flow to flow called flux, right? Electric flux, water flux. What is water flux? V into A. That value changes with the angle. When the angle of the area changes, the flux through this also changes. Therefore, the general expression for flux, as I explained you like this, becomes AV cos theta. Final explanation of this, students, very simple. You listen once again carefully. If I hold area just perpendicular to direction of flow, how do you show it? Blue piece of chalk, direction of flow. Pink, normal to the area. Normal is very useful here. These two are parallel. Angle theta 0. In that case, how do you find flux? Value of water flow at each point? A. Into area gives total flux. The problem arises when you rotate the area like this. I have shown. Was initially like this, you have turned it through an angle theta. When you turned it through an angle theta, you can do a construction. There is opposite area, adjacent area, hypotenuse, original area. I want only adjacent. Why? Because only this much area now available. Water only flows through this area. Remaining water below this flows outside. This is flowing outside the area. Now flux is less. Per unit area cross section same value, but effective area only less. What is effective area? Adjacent. What is adjacent? Hypotenuse A cos theta. So effective area is A cos theta. Value of water at each point V only. That is V into A cos theta. V into A cos theta. This is general expression for flux. And it takes care of all the orientations. Orientation here 0 angle. Angle increases becomes 90 for all these cases. This is applicable. Even for obtuse angle, it is applicable. We'll see such cases next. So, I'll rub all this. I'll remove all these cases. Just remember this much. I'll remove this. What is flux? Flux is value at each point into area. When the orientation of the area is not, orientation of area means what? Whenever I use the word orientation of area, what do you think? Always we imagine normal to the area. If the normal to the area, this one, normal to the area, not parallel to flow, make some angle like this. See here, make some angle like this. The value of flux changes. Effective area available decreases. In that case, we write relation AV cos theta. Students, you watch this video thoroughly, carefully. Play this 2-3 times. Like this only you have to think. This is how we explain general expression for flux. Flux is AV cos theta. What is theta? Theta is the angle between normal to the area and direction of flow. Flow direction is like this, normal. Right? Blue normal flow and or pink color normal. So between these two angles. When they are in the same direction, what is the orientation of area? Area is normal to the flow. When the angle, if I hold like this, area is inclined with respect to direction of flow. Right? That's the idea we have to remember. Somewhat like this. Flow, somewhat like this it is. We have to remember. So this is the general expression for flux. Flux. What flux? Water flux. The same thing can be explained for gas flux. Flux of gas through a cross-sectional area. It's very, very important idea. Now let us come to our topic, that is electric flux. What is electric flux, students? Instead of water flow, now let's consider electric field. Let me continue with the same thing, but change a simple arrangement. Look here. So this is sheet. This is a sheet, right? This sheet I am charging. If I put charge over this entire region, rectangular like that, if I put charge over this, say positive charge, this is what we called in the last video charge distribution, not point charge, charge distribution. In this charge distribution, students, the electric field influence is like this. In the previous example, water flow. Here, electric field coming out of this. Electric field coming out of this. Let us suppose it is uniform, has same value all around for simplicity. What is the value of field at each point? Value of field, initially, previous example, V was the volume of water flowing. Now here, how do you find electric field? Electric field at a point is found by placing unit positive test charge at that point. Since these are positive charges, when I place unit positive test charge here, it experiences force outwards. Why, students? Very simple. This is unit positive charge plus repelled by this positive charge. That's why the electric field is to the right. Now the word flux through the entire area. Same value field here, everywhere. Let us suppose uniform field. Same value, same direction. Right? In that case, the total, not water flux. What is that? Electric flux. Total electric flux. Phi, not V, it is E. E into E. E into E. Right? In fact, it is E dot A. As both are vector quantities. Electric field has a direction value. Area, we have assigned a direction. What is direction of the area once again? Direction of area is normal. Normal to the area. So, if you measure angle between normal to the area, for this yellow area, electric field and normal to the area both are in the same direction. But for this, electric field E, not flow. Electric field is in the same direction, whereas area makes an angle theta with respect to the direction of the field. In that case, if area is turned through an angle theta, the new new area available is A cos theta as I explained you here. Same thing continues. Therefore, new flux is VA cos theta, and this is general expression for flux, right? Here instead of V, what do you write? E. So generally, what is flux? Flux through what flux? Electric flux through an area of cross section. An area of cross section phi equals to electric field E dot A. There is a cross product, dot product. Last year you learned. What is A dot B? A dot B. What is A dot B? Value of A, value of B into cosine of the angle between them, right? This is what you learned. Therefore, here you write, what is E dot A? Value of E, value of A into cos theta. But students, you remember this A cos theta. What is this A cos theta? A cos theta is component of area available for field, like this. If I hold it like this, electric field is towards your right. If you are watching video like this, towards your right, the entire area is available. But if you hold it like this, a part of the area available. How do you do calculation? As I explained you earlier, right? This is initial orientation. If I lift it up to a certain value, this is new orientation. Now you project. Project means draw perpendicular. Only this area effectively available for flux. What is that area? Adjacent. This theta. Adjacent is hypotenuse. A into cos theta. Very simple, right? Students, the flux means to flow. What is flowing? You feel as if electric field flows out because it has direction, right? That value changes with orientation of the area. Students, whenever we use the word flux, you think electric field over an area, electric field value over an area. How do you know it? Electric field value into area, right? And this idea very, very convenient for us to calculate electric field at any point. By evaluating flux, you can find field. And this method is very useful. Why? You apply Coulomb's law only for point charges. For large charge distribution like this, cross section, charge over a cross section, Coulomb's law becomes ineffective. In those cases, by finding flux due to this charge distribution, we can find field at one point, right? So before I move on, you remember this much. What is electric flux? Flux is a dot product of E and A. Why dot product, students? Because how much area is available for electric field? How much area means A cos theta. When cos theta comes into the expression of product of two vectors are area and electric field, then it is called dot product. Last year you learned, right? So E dot A is EA cos theta. This takes care of all the orientations from 0 to 90 degree. When is flux maximum? When the angle is 0. When is flux minimum? Minimum is 0 when angle is 90 degree. When angle 90, flux 0. When angle 0, flux maximum. What is maximum? E into A. Value of E into value of A. That's it. Once you define flux like this, the next job is to find SI unit, students. Very, very important. Sometimes they ask for one mark question. What is SI unit? SI unit of flux phi equals to, see, electric field. What is unit of electric field? Force per unit charge. Force Newton per divide charge Coulomb into area. What is area? Square meter. What is unit of cos theta? No unit. Why? Okay, students, we will now have a quick revision of what we learned so far. That is electric flux through an area. What is that? E dot A, vector E dot vector A, that is EA cos theta. When you write this, how do you visualize it, realize it. See, there is a point where electric field is in this direction, theta, angle theta. This is the direction of electric field. Now I will consider an area of cross section around this point. Around this point, I consider an area of cross section. This one. This is the area of cross section, students. Area around this point. Suppose the area A. What is the direction of the area? Area direction is always normal, students. This is normal N. Now the angle between the direction of electric field and the normal is theta. Now you find the value of electric field over this, draw perpendicular. You draw perpendicular, this angle theta. If you find the value of E along this direction, this is E cos theta. You have done several times. That's called resolution. We did in this year last two videos, 15 and 14, to find electric field due to a dipole on the equatorial line, right? You are finding the value over this adjacent side is hypotenuse into cos theta. So what is flux through this? Value of field along this direction, E cos theta into area. That's one thing. Or you can consider electric field direction. This is the area normal. You find the value of normal in this direction, draw perpendicular. This is area A into cos theta. Area value in this direction A into cos theta, right? In the direction of electric field. Because you can write EA cos theta or A into E cos theta. Both are true here. A cos theta is projection of area in the direction of electric field. Or E cos theta is projection of E in the direction of area. Either way, you can explain. This is how you have to think. This is the flux. Electric field along the normal into area. Field value at one point is E into area gives flux. But if the area makes an angle theta with the electric field, you have to find the value of field in the direction of area. That is normal. E cos theta into area. Very simple. Now, why this idea? Because Gauss law involves such explanation. That is flux concept. Why Gauss law, students? You have already a law which deals with force between two charges, the 2 point charges, Coulomb's law. Then why this? The major limitation of Coulomb's law is applicable only for point stationary charge. Point charge is very important. For a large charge distribution like charges along a straight line, charges on a surface, charges in volume, the law cannot be applied. For such situations, a Gauss, genius, a prince of mathematics, developed an important idea, that is flux, electric flux idea. By finding electric flux, we can evaluate for electric field. I will show how to arrive at this statement. You are going to write statement of Gauss law. You are going to write statement of Gauss law. Statement. First of all, I will show how the Gauss law is arrived at. You can obtain easily by using Coulomb's law. Very simple explanation, right? I will show you that part of the explanation proof you need not prepare for board exam. You should know how it is. This statement state and explain 3 marks question. We will practice that. Let us see a note part. See, explanations are all you have to remember, friends. Only for board exam. Okay, we will learn for board exam. I have given notes, precise notes only for board exam. While explaining, I will explain the textbook. And I will give how much you have to remember for board exam. Yesterday I did, right? In the case of torque, acting on a dipole, electric field on axial line, equatorial line, all that I explained. Similarly, let's suppose there is a point charge here. A point charge. Students, this point charge influences the entire region through its field. What is that field called? Electric field. Let us suppose there is a point. You place a unit positive charge here. What does it do? This repels unit positive charge in this direction. Draw these two, extend this direction of field here, right? Electric field direction. Now, the distance between these two, say R. What is R? Distance between the point positive charge and this. Now, the students, idea is you choose this distance, separation between the point charge and unit charge are as radius, and draw a sphere. On the board it is circle, but you can draw a sphere in space. In space, right? At the center you have a charge for simplicity. Even if you place anywhere in this region, this law is applicable. This Gauss theorem is applicable. What I am going to show is Gauss theorem. That is applicable for any position, not only at the center. Now the charge is at the center. Okay. Now the field is here, anywhere around. All around there is electric field. This is called spherical symmetry. Symmetry, very important concept in physics, students. Symmetry means what? See, distance between this and this same, this and this also same, but direction different. So the electric field value depends on charge inverse proportional to distance, square of distance. Charge same for this and these 2 points. Distance also same. The field value same, but direction different. Here unit charge will be repelled away like this. When the charge is here, repelled away like this. When the charge is here, repelled away like this. Right? So student, I have shown only 4 points or 4 points where electric fields point outwards. All the 4 electric fields are different direction wise. Value wise they are same. Then how do you add total? You can find electric field here to away, here to away. What is the total electric field over the entire surface area? That is sphere. Over the entire sphere, spherical, I write here, entire spherical surface, imaginary surface, what is the total electric field? If you find total electric field over the entire area, that is called flux. You cannot add the electric fields directly if you call this E1, this E2, this E3, because direction is different. For such situations, the concept of flux is useful. Now, how do you evaluate flux, students? I will show you. Very important. Observe carefully. Now, you consider a small cross section here. A small cross section, right? See, the area of cross section of this is some ds. Why you are writing instead of A, you can write dA also, dA, ds. I am using S for area, small area of surface area. Surface, first letter S, that's why ds. That's. Here too, I can consider the same area, ds. Here too, area of cross section whose value ds. Here too, small cross section ds. Means I am dividing the entire spherical surface into smaller areas, like patches of a football. I will show you now. Look here, students. Can you see a patch here? One patch, area ds, second one, third one, fourth one, fifth one, like this. In each patch, the electric field almost radially outwards, right? If you consider this here, the normal to the area and the electric field both are in the same direction, right? Then what is flux here? Flux is E into A into cos theta. As both are in the same direction, what is the value of flux? I write d phi. Why d phi? Phi flux. D implies very small. Why very small flux? Small area. So I can write E into ds into cos theta. What is cos theta here? 0 degree. Therefore, d phi here is E into ds. Electric field value into area. Theta is 0. What is cos 0? 1. Same story. Flux here, d phi is E into ds. You are not writing E1 here, E2 here. Why? Electric field value same, direction different. What is flux here? Flux here is E into ds. What is flux here? Here also d phi E into ds. Right? All around. Do the same for this. All patches. You continue the same procedure. Then add all the fluxes. Remember, students, flux, electric flux or scalar. Why scalar, students? I did not mention initially. Thinking that you know dot product of two vectors is a scalar. It is a scalar. Scalars can be just added. What is total flux? Total flux, electric flux is equal to, what is that? Total flux is equal to summation. I write here add this flux with the next area, with the next area, with the next area. Like this, we are adding electric flux at one point into ds. What is EDS? Flux at one point. You are just adding that. Students, field value at all the points, here it is E, here it is E, here it is E, everywhere the field value E. So you are not adding, it is a constant. What do you add? You add always the thing that changes. What is adding here? Area. First you consider this area. You add this area with this. You add this area with this. You add this area with this. Right? The process of adding explained by using this symbol. What did you call it? High school? Summation. This is called summation. Right? Summation. So the symbol summation here, flux phi equals to, what is the value of E? Electric flux. Can you tell me what is flux? I write here electric field. Sorry. What is electric field at one point due to a point charge? 1 over 4 pi epsilon 0 into charge Q divided by R square. Am I right? This is the value of E. Then what is summation ds? Tell me students, what is summation ds? Summation ds is, yes, if you just go on adding all the patches, you get what? You get a sphere. Summation ds, area of sphere, spherical surface. What is the area of a sphere? As you learned in high school, 4 pi r square. So write these two values here. In the place of E, 1 over 4 pi epsilon 0 into charge Q divided by r square into, what is ds? 4 pi r square. 4 pi cancels, right? R square cancels. You are left with what? 1 by epsilon 0 into charge enclosed. So what is the conclusion? Therefore, the conclusion is left side phi flux 1 by epsilon 0 into charge enclosed. Q is charge. That is the result of flux in terms of charge and a constant for electric field epsilon 0. That is popularly known as Gauss theorem. He showed that it is a symmetrical object, sphere, but the same can be explained for any surface. What do you do? You imagine a surface with a charge inside, then you applied Gauss theorem. Then you applied the electric field expression, that is 1 over 4 pi epsilon 0 q by r square, and found area, summation of area as it is a sphere. Just you go on adding the areas of the patches. If you cut these patches separately, then start joining, stitching all, like patches on football, right? If you join all the patches, what do you get? Total surface area of sphere, which is 4 pi r square. So 1 over 4 pi epsilon 0 q by r square into 4 pi r square is 1 by epsilon naught into q. What is that? The flux. What is flux? 1 by epsilon naught into q. That is statement. Very important. You have to explain this in words. How do you explain in words? I will tell you. You have to explain total flux. You have to write this statement. Total flux through surface, through a closed surface enclosing an amount of charge, Here, the total flux through the entire surface, closed surface, it is not open, completely closed all around, which encloses a charge, is equal to 1 by epsilon 0 times charge enclosed by it. This is very important statement, right? They'll explain they'll ask you to explain this. State and explain Gauss theorem. What's Gauss theorem? Gauss theorem is total flux through a closed surface enclosing an amount of charge. You think of the situation. There is a charge. You have enclosed the charge by using a closed surface which is spherical. Spherical has symmetry, right? That's what symmetry means. Distance from here to here, same as that from here to here. Here to here, here to here, right? You know about sphere, symmetry. But even if you consider any shape, evaluation of flux, bit complex. We have to use tougher mathematics parts like integration we have to use. We will learn about that in coming class in mathematics. Let's not bother about how to evaluate. Totally, if you find flux through the area, entire area which encloses charge, what do you do, students? You consider a sphere, put a charge inside, right? Then he says there is flux coming out, electric field is coming out. If you evaluate flux over the entire surface area, mathematically, then you get 1 by epsilon naught times the charge enclosed. I showed for 1, very simple. Total flux is summation of the flux E ds. What is E? Electric field at one point. What is ds? Total area. You are adding y. There are large number of such areas like this. When you add, electric field remains the constant. So you take it out. What are you adding? Surface area. If you complete adding surface area, you get area of sphere, which is 4 pi r square. What is field at one point? Coulomb's law. Field at each point is this 1 over 4 pi epsilon naught q by r square. Put the values here. Here r square 4 pi cancel, phi equals to 1 by epsilon naught into q. So, how did he explain? The condition, there must be a charge enclosed by the surface over which you find electric flux. That flux is equal to 1 by epsilon 0 times charge enclosed. Total electric flux through a closed surface enclosing an amount of charge is equal to 1 by epsilon 0 times the charge enclosed by it. Very, very important, students. Right? So, I will show it once again in the next video, this part. You remember this statement, right? How to apply this statement, how it is used in finding electric field in different cases. We'll learn in next videos. This is the statement. I'll explain you how to apply these statements, and also there are 3 applications of this Gauss theorem. Very, very important. We will see in the next videos.